Okay, today I want to talk about some more integrals via residues. A couple more types of integrals that you may have been trying to work with in some of the homework. So for instance, what if you had an integral like this? X sine x over 9x squared plus 4, 0 to infinity. So first of all, of course, having the sign suggests putting in a term like e to the ix, because if you looked at this integral, and write this as cos x plus I sine x, you could break it up into real and imaginary parts. So this guy you'd recognize as the imaginary part of this integral. So actually, if you did this integral, you'd sort of get two integrals for the price of one, right? By taking real and imaginary parts. So to do this integral, we change the x's to z's and look at this complex integral. Now, we really wanted to integrate on the real line, but we're going to do it by complex. We're going to integrate like we did before. We're going to integrate over a contour that looks like this. We're going to take an interval of the real line and then a semicircle, but coming back to the beginning. So we think of rho as some very large real number. So this is a big piece of the real axis, and then that's the semicircle. So we're going to call this part C1 and this part C2. So the relevant facts to doing an integral like this are that we have a ratio of polynomials and an e to the iz term. And with these polynomials, what really matters, so this is a little bit different from the last video, is that the degree of q is at least one more than the degree of p. In the last video, it had to be two more, but in that video, we didn't have this term. And this term allows us to change the 2 to a 1. All right, so here, the degree here is 1, the degree here is 2, so we're satisfying this. And again, I'm assuming the q has no zeros on the real axis, so you don't encounter any singularities as you integrate along the real axis. So the sort of theoretical result that's a bit complicated, takes a bit of work, so I'm not going to worry about this, is that under these conditions, when you look at the integral along this semicircle and then let rho go to infinity, this integral goes to 0. All right, so let's accept that. So that means the integral over this closed curve as rho goes to infinity, just in the limit is just the integral over the x-axis, because this part is going to 0. And of course, when you integrate just over the x-axis, these z's are the same as x, and you just get this. And this is what we are looking for, this integral. That's what we're looking for, because, well, that would be, like in our example, that would be this one. And then we would be interested in the imaginary part. Okay, so how am I going to calculate this? Well, remember, the point is that if rho is big enough, then this is going to be some huge curve, and it will enclose all the singular points. Now, there's, of course, in this example, there's only two singularities, where the denominator is 0, and that's plus or minus 2/3 I. Plus or minus 2/3 I, right? When x squared, or when z squared is minus 4 over 9. So that's 2/3 times I, or plus or minus. So there'll be a singularity sort of up here and down there. So we're just enclosing the one singular point at 2/3 I. The residue can be calculated. Since this is a simple pole, the limit as z goes to 2/3 of an I, z minus 2/3 I times this function. All right, now the point is that this can be factored. If I factor out the 9, I'll be left with a z squared plus 4 over 9, and that'll be z plus or minus 2/3 I. And so then these will cancel, And then the remaining terms, I'll just plug in z equals 2/3 I. So I plug in 2/3 I, e to the I 2/3 I, and then these cancel. And then here I plug in 2/3 I, so I get 4/3 I. So I just get this, which simplifies to e to the minus 2/3 over 18. So that's the residue. So the integral around here is 2 pi I times that residue. So there's 2 pi I times the residue, which is this number. So this value here is that integral. And that's independent of rho. Once rho is big enough so that we contain the singularity up here, then the integral over this is always this number. So when we let rho go to infinity, it's still that number, but this contribution goes to 0, and this contribution tends to the integral from minus infinity to infinity. So end up with the integral from minus into infinity. So it's just on the real line, so it's all just x's, is this number. But remember here, we were interested in just the imaginary part. So the imaginary part is just the pi over 9 e to the minus 2/3. So that would be our integral. Now actually, if you wanted to solve this problem, keep in mind that this function here is an even function because because the denominator is even, but both of these are odd. So if I replace x by minus x, both of these change sign. So the result is that nothing happens. So this entire expression is even. So the integral from minus infinity to infinity is really just twice this integral. So if I wanted this integral, I could just take half of that. That's the idea. All right, so that's an example where we have the denominator only one with a degree is 1 higher than the numerator, but then we needed a sine or cosine term here so that we could use this result. Again, without this, like in the previous video, without this term, you'd need the degree of the denominator to be at least 2 more than the numerator. But with this exponential term, I can get away with 1 more. All right, so that's an example of that nature. Then let me show you another kind of example. And that's one where we have a singularity on the real axis. So far in our examples, all the singularities were above or below the real axis. But what about something like this? All right, then you're going to get a singular value at 1, and then from this guy, plus or minus I. So we have actually 3 singularities, I, minus I, and 1. And we want to do this integral. All right, so if you've looked in the book at all, you see they take an approach like this. Instead of just integrating straight through, what we're going to do is we're going to avoid this singularity by taking a little detour going around it. So instead of going from minus rho to rho straight, I have to be careful at the singular point. So I go C1 takes me very close. C2 takes me in a nice little semicircle like that. C3 takes me the rest of the way. And then C4 is the semicircle. So C1, 2, 3, and 4 is this closed contour. And you can see here it just encloses one singular value, I. All right, so I'm interested in this integral. And I'm using capital gamma to be this entire curve, C1, 2, 3, and 4. So the line integral about gamma is 2 pi I times the residue at I. Okay, the residue at I, again, it's a simple pole because I could factor this. I could factor this as z plus I and z minus I. So I get these 3 different singular values. So if I multiply by z minus I, these cancel. And then I basically replace z by I. So it's I minus 1, I plus I. So I get this as my residue. And then 2 pi I times that gives me this. And if I multiply, I could multiply and divide by 1 plus I, just to simplify it, and I get this value. So this value, this is the value of this integral. And as now we think of rho getting bigger, 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 but we also want to think of the radius of this tiny little semicircle is getting smaller and smaller. This is a semicircle of radius r. So I'm going to want rho to go to infinity, but I want r to go to 0. So I have to worry about both of those. So first of all, and there's 4 parts. So first of all, the semicircle. Well, as we've seen before, that limit will go to 0. All right, so in the limit, this guy goes away. The C1 and C3, so this will start further and further out, and it will go and get closer and closer to 1. That's for C1, and then C3 will start very close to 1 and then go a really long distance. So in the limit, as rho goes to infinity and r goes to 0, we get what we call the principal value of this integral. Again, sometimes these integrals don't don't converge near the singular point, and you're calculating what calculates as a principal value. So certain infinite behavior on the left side and the right side can actually cancel out, and you end up with a finite integral. So these two together give you the principal value, and then that leaves C2. The limit of the integral is C2 as r goes to 0. Now the claim is, and I will prove this claim in a minute, that when you do this, you get minus pi I times the residue here. Okay, and we're using the fact, this is going to depend upon the fact that this is a simple pole. If you had a pole of order 2 or higher, then none of this is going to work. But here we have a simple pole at 1. So the claim is, in that situation, this is minus pi I times the residue at 1. And what's the residue at 1? Well, it's the same thing as I did up here, except I apply, it's z minus 1. I look at z minus 1 times the function, so it's z minus 1 over this, and look at the lim. The z minus 1's cancel, and as z goes to 1, this will go to 2, so you just get that answer. So see, this was minus pi I times the residue. So now when you put all this together, the principal value, remember, the sum of these 4 integrals was given by 2 pi I times the residue at I. So that equals this number. But then we pass to the limit. The semicircle went to 0. C1 and C2 went to the principal value, and C1 and C3 went to the principal value, and C2 went to minus pi I times the residue. So when you put that all together, you get that this principal value is 2 pi I times the residue at I plus, because this guy is brought to the other side, pi I times the residue at 1. And you stick it all together, you get this value. So that's why you see in the book, in situations like this, you'll get this principal value is 2 pi I times this sum of the residues above the x-axis, things that will be enclosed by this curve, plus pi I times the residues on the x-axis. If there had been more than one pole on the x-axis, I would have had to do this little thing at several points. Each one would be the same kind of contribution. So it's 2 pi I times the sum of the residues above the x-axis plus pi I times the residues along the x-axis. And again, it's important that these singularities be simple poles. So all I have left to do is verify this claim, and that's what I'm going to do here. So this is along the x-axis. I have a point A, which is a real number, and we assume that f of z has a simple pole at z equals a. And then the claim that I used here was that the line integral along this semicircle. And notice this semicircle is oriented in the opposite way that it's usually oriented. That's why we get the minus sign. And the claim is this limit is minus pi I times the residue at a, if it's a simple pole. Because if it's a simple pole, then you can write it like this: an analytic function divided by z minus a. All right, so I'm going to use that fact. And g is analytic at a. Now I'm just going to parameterize this semicircle. Z equals a plus r e to the I theta. Theta is going to go from pi back down to 0. Right here it's pi, here it's 0. dz is this. So when you parameterize this whole thing, you get the integral from pi to 0, and the f that'll be g of a plus r e to the I theta over z minus a. Z minus a is just this part, r e to the I theta. The dz is I r e to the I theta d theta. All right, the r e to the I theta cancels. The I can pull out. I'm going to pull out a minus sign, so I'm going to change this limit to 0 to pi. All right, so that's where my minus sign comes from. I'm left with the lim as r goes to 0 of the integral g of this expression d theta. But the point is, think about what happens as r goes to 0. You're looking at values of g getting closer and closer to a. You're always looking along these semicircles, but the semicircles are shrinking down, converging on a. So in the limit, these values are all just g of a. Then again, I get from the integral times pi. So I end up with minus I pi g of a. But what's g of a? I claim g of a is just the residue. And that'll complete the proof of the claim. Right, it'll be minus pi I times the residue. See, g is analytic, so it has a power series. And so f is what? It's g over z minus a. So I divide each of these terms by z minus a. I get g of a over z minus a, then I get g prime of a, then I get g double prime over twice, then I get 1 power z minus a. So what you see here, you see you've taken a power series, you've taken like a Taylor series, a power series, and divided by z minus a. So what was the constant term now becomes the coefficient of the z minus a term, which is by definition the residue. So that shows that this limit is minus pi I times the residue. And that's what I used back here. That was my claim, minus pi I times the residue. But again, this proof only works for a simple pole. See, if it wasn't a simple pole, then I'd have a higher power of z minus a here. And, this proof would fall apart. You wouldn't have convergent integrals, so you'd have a problem. But in our example, we do have a simple pole, so we're always going to need to have simple poles along the x-axis. Anyway, that completes the proof of this claim, so that's the proof of this integral. So that covers the kind of integrals in the book where you have some kind of singularity along the x-axis, or maybe several singularities. But if they're simple poles, then this method will work. So basically, it's 2 pi I times the residues above the x-axis, and then just pi I times the residues, some of the residues along the x-axis. So hopefully that'll help you with some of the problems you're supposed to be working on for homework. And I'm going to do one more video. There's one more type of integral that I want to give you an example of. I know it's on the homework, or there's one like it on the homework. So I'm going to post one more video, hopefully tomorrow or the next day. So be on the lookout for that, and that'll probably complete the videos for the semester. So until then.